Hello. Today we're going to look at floating point precision from section 1.7. Now before we get into the terminology in the textbook, I want to go over some more basic definitions of error just so that we're clear on what it means to have an error or a relative error. The first is that error equals true minus approximate. And we'll often use a capital E or perhaps an epsilon to represent error. And the error, or sometimes called the true error, is most helpful when you have two quantities or two sets of data that are measured using the same units. So for example, you did two runs on an experiment that uses the same units. You can compare the errors. That makes sense. Relative error, which is often written using a subscript r, is equal to the error divided by the true value. So we often will write it as the true minus approximate. I'm going to approximate the approximate word, but just approx, divided by true. There we go. Okay. So those are two basic definitions. Now, relative error is actually more useful because you can compare the relative error of your experiment to someone else's experiment on something entirely different, where the units don't have to match. Because relative error is based upon a percentage. So we often will think of this times 100%. So if you have a relative error of 0.032, that really just means 3.2% relative error. Okay, so that's what it means here. Now, one caveat in these definitions is that we are approximating because we often don't know the true value. Well, that is in terms of when you're solving something. So when we use approximations to solve an equation, we're doing it because we don't know the solution. Whereas if you're just taking information and storing it, you know the information and you make an error by storing it, say, on a computer. You can create error that you know based upon storage, whereas you can create error that you don't know based upon solving an equation or a problem using an iterative method or repeated algorithm. So that's one thing to point out. That practically speaking, a better approximation is often used instead of the true value. Now, what does it mean by better? Well, it depends upon the situation. What better approximation do you have at hand? Do you have access to the best approximation? Then use that. If not, use what you have that is better. For example, when estimating an unknown true value with a sequence. Let's call it x sub n of increasingly better approximations. Then, a practical calculation of error that we use is the next best iteration minus the last iteration. And to take that approximate away, we'll just label it as something different. We'll say the error at the nth iteration is best approximated as the next best approximation minus that approximate value. And as you get closer and closer and closer to the true value, this one's a little bit closer than that one. You're assuming that you're getting increasingly better. So that's a big assumption. But it does allow us to practically estimate the error when in reality we cannot. And to go along with it, we can estimate the relative error at the nth. Now maybe let's use, instead of a set here, let's use a superscript. The relative error at the nth step can be estimated as x sub n plus 1 minus x sub n, all divided by the true value we're approximating as x sub n plus 1. And these are known as the approximate error and approximate relative error at the nth step, in a sense. So these are the kinds of steps that we need to take when our goal is to know how far we are off from some true value, even when we don't know what that true value is. We need to estimate our steps. Why is that important? Well, we often will describe and implement algorithms that will go with a stopping condition of stop when you're close enough. And if you program an iteration and you tell it to stop when you're close enough, but you don't know what the value is you're trying to approximate, it will never end. So you have to have some way for it to estimate when it gets closer and closer. And so one way is to use these approximate errors and approximate relative errors. And they are good definitions as long as we have a sequence of increasingly better approximations, which means that your estimate, your algorithm, is getting closer to that true solution. So as a layer of abstraction, we have a detail that allows us to compute or tell the computer when to stop, a stopping condition. And then we step back and we have to, as the programmer, know, or at least analyze the equation to know when your approximations are getting better, when they are converging. So we're interested in those intervals of convergence. What is the radius of stability? Things of that nature. Okay, so here are basic definitions. For addition and subtraction, the magnitude of the error in adding two numbers which are approximate to the true values of those numbers is less than or equal to the sum of the errors column error 1, error 2. Just good that we identified those. That we identified the superscripts for the approximate, relative, and regular errors before. So if how do you say this? Where E1 equals our first say x minus x1. So the true minus the approximate. So this is the approximate value we have. Here's the true value we don't know. Here is the, or no. Here is the error. Error 2 equals x minus x2. So again, it's an error related to a second approximate. And E itself would be, well, x1 plus x2. How far is that from 2x? Or x plus x. The true value of their sum should be x. The approximate value of their sum is x1 plus x2. What is the error? Now that one's pretty straightforward. We can prove it using a nice triangle inequality, because either the errors are both on the same side and they just add, or they're one's on the left and one's on the right and they cancel a little bit. If they add, we just get the straight sum. If they cancel a little bit, it's a little bit less than that sum. For multiplication or division, our bound is not on the error itself, but on the relative error. And it's very similar. The relative error of the first one plus the relative error of the second one, where ER1, relative error again, is x minus x1 divided by x, the true value, that's relative error. ER2 would be x minus the second approximation divided by the true value x. And of course, the relative error itself is the error in multiplying the two numbers together. Now in this case, they're both x, so the true value should be x squared, but instead we get x1 times x2. And to get a relative error, we divide by the true value. And that's, of course, for multiplication. It's similar, but a little bit different. For division, you just end up dividing. And this one, of course, is for addition. And you could rewrite it with a slightly different form for subtraction. The main idea is that when you're tracking how the errors change or propagate, if you're only adding and subtracting, then the errors themselves grow by adding up. But if you're multiplying or dividing, it's not the errors that end up being added, it's the relative errors that end up being added. So that's the main difference that we'll have to track. checking the propagation of our errors. Okay, so now let me reset the board.